Okay, Darren, maybe you can start with the survey paper presentation.
Yeah. Good afternoon, everybody. So I'll be presenting on the survey on adaptive random testing. So these are the authors. So we have 3 master students and 3 PhD holders. So all from various institutes, and they all have interest in software testing or software maintenance. Yeah. One from Monash University as well. Sorry.
Okay.
So we go into some background first about the topics before we dive into what the paper covers. So we cover
by the way, where is this paper published?
Oh, this paper is published in IEEE under the Transaction and Software Engineering for this year.
Okay, TSC this year. Okay.
Yeah. So we'll just go through some background first about these 3 terms. So as defined in the paper, software testing typically takes this scenario. So we first define the testing objectives. We choose the inputs in this case. For the software test cases, we run the test cases and then we analyze the results, compare it with a test oracle, tells us what the correct results are supposed to be. So this is the typical scenario that we have for testing. Next, we look into one particular approach for such testing.
By the way, Darren, have you prepared some questions for the audience?
Yeah, they'll be later on in the slides.
That is great.
Yeah. So random testing is one such approach to automated software testing. So in this case, we generate random inputs and these random inputs constitute test cases. And so this is of course a very basic approach, and they can be, and there are improvements to this approach. And one such improvement is of course adaptive random testing. So this idea is that okay, we skip this one. Sorry. Yeah. So the idea is that failure causing inputs are often clustered, and what this means is that in the input domain, a failure causing input, the input that causes a test case to fail, in that it produces a different result from test oracle, is often close to another input in terms of in this case usually Euclidean distance. So this means, for example, if you consider the test input to be some kind of a vector, maybe a numerical vector, you typically find other failure causing inputs close in terms of Euclidean distance vector wise to this failure causing input. And so with this knowledge, this is an empirical observation noted by many different authors across different papers. With this idea in mind, you have an improvement on random testing called adaptive random testing, where we try to have a more even spread of the test cases across the input domain. And so this will hopefully find more failure causing inputs than random testing itself, which may form clusters just through random choice. So this is the idea behind adaptive random testing. They want to improve on it by having a more even spread. And the way they have it even spread is through 2 processes. One is for random generation of test inputs. The other is to ensure that the randomly generated test inputs are evenly spread out across the input domain.
So will you please more specific on the term of adaptive? So given the process, right? So the overall idea is that we want to generate a test case or generate the input, which can evenly distribute among all the space, so that we can discover as many failures as possible. So can you link the term adaptive to such an idea?
Yeah, sure. So the idea that adaptive here refers to the fact that adaptive random testing uses some information about the test cases generated to generate the next test cases. So in this case, for example, if you generate one test case first, they might check whether or not it's failure causing. And if it is failure causing, you might generate test cases closer to this input, versus if it's not failure causing, you might generate test cases further away from this input. So in this manner, it's called adaptive because it adapts to what it generates and it uses that to generate more test cases.
Yeah, so basically it was usually adaptive random testing is somewhere close to the optimization, and or like the search algorithms or a heuristic optimization problems. So we will keep generating the test cases, and some of the test cases we will run the test cases. We can get the feedback by the runtime information of the generated test cases, and that feedback can guide us to further generate another test cases, which can achieve maybe a better coverage or etc. So the difficulty or challenge here is that how do we define a certain feedback to run after we run a certain test cases? Okay, let's keep going on.
So the paper's approach is that it will cover these 6 topics. So the first is an analysis of 140 different papers on adaptive random testing between 2001 and 2017. Next, they'll classify the different ART techniques given in these papers. They also summarize the application areas for ARTs. In this case, each paper typically apply an empirical study of some sort, ART on certain things. So maybe it's real programs, industrial scale programs, simulations, different application areas. And they also analyze the experimental evaluations of ARTs. In this case, the kind of studies that people take to evaluate the effectiveness of ART under certain conditions. It also addressed some misconceptions about ART. So these certain misconceptions authors have noted across different papers. And finally, identify some open research questions. These are some challenges that still remain open in the field. So first, we talk about the summary analysis of the ART papers. For this, the authors.
By the way, so for this work, this what I think we should go also think beyond the testing. So this is basically a survey paper. So if in the future, maybe you find Xiangling Ruofan, you want to write your own survey papers, maybe you can follow the same template. And right, you find we once discussed one, we want to write a survey paper. And in order to write a survey paper, what kind of template we want to follow. So we can also follow the style, right? What kind of papers we selected, where to select the papers, and how do we provide the taxonomy of this technique, and what criteria to derive such a taxonomy, and then what kind of findings and what kind of evaluation can be done, and also pinpoint a point and the future research direction. So this is basically a way to write a survey, and usually the survey paper can derive very high citations for you. Okay.
Yeah, so for this analysis, first the authors selected papers from 5 online literature repositories. So these are the 5. They chose these particular repositories because these repositories are known to be well known, and they often hold important research papers. This is the author's justification for choosing these 5 repositories. So from these 5 repositories, the authors just searched adaptive random testing and titles or keywords containing the words random test. And finally, they did one additional search in Google Scholar just to make sure they didn't miss out any papers that are not from these 5 repositories. And in total, from these repositories, after filtering, so they filtered according to some characteristics here, for example, studies not in English, studies not related to computer science, summaries, for example, such as keynote records, studies that are full text, so they can't fully analyze these studies, or masters or PhD thesis. So these are probably like a cutting edge research that they don't have analysis for. So after this reduction, they reduced the original 1,276 papers to 138. And then they checked the references of these initial 138 papers and found 2 more papers to add in. So there's a total of 140 papers, as mentioned before. And of these 140 papers, so they ran some analysis. The first is that the number of publications per year, they noted a spike in 2006. I'm not quite sure why. They also didn't mention any particular reason for this, I think. But they mentioned overall that they see a strong linear growth. And this is a good news because it means that the field is growing and that it's improving, and expect to see about 180 papers by 2021.
Yeah, I think this is very good for writing a survey paper. We're showing that why, and this is one of the motivation for why we need to do such a survey, right? And now there's other survey, but we can find that this area, and it is actually a growing area. So with these growing areas, and this means that it is a very hot topic. So given the hot topic, if you want to join, so the more popular the community, the more popular the topic, the more likely new researchers will look into this area. So we're going to see, and so we need such a survey, and our survey actually conclude all these papers, and also we also show that how we collect these papers. So that is really helpful to motivate this work. Yeah.
And next, they talked about the geographical distribution of where these papers come from. So I find that, not oddly enough, not for any particular reason, Australia is the most prolific region apparently in terms of ART research. And they also noted that ART research is concentrated in a small number of countries spread throughout the world. So they mentioned that this might be of interest to people who want to collaborate on ART research, for example.
So yeah, so but you can see from the one with the most publications, so maybe people still need to. So if I was a reviewer, so I will not mention deliberately, but I will further ask to calculate the rank. So maybe there are different countries have a different rank. So if we want to look into the top authors, so we may also look into the rank of papers they publish, right?
Yeah, maybe not all papers are equal. So some, even though you may produce a few papers, may be very influential papers. So that's also one possible thing to look at. Yeah. Okay, and then they mentioned the distribution of papers between different types of publications, for example. So conference versus symposiums. Conference symposiums were the most, followed by journals, and finally workshop papers. So let's mention this as a side note as well. And this, of course, just some information about the top venues and minimum 3 ART papers. The authors didn't really elaborate much on this. Just mentioned the data briefly in the side notes.
They're looking to the QSIC most.
Yeah.
Yeah, I think that'll be a problem. Why there's no ICSI there? There's no ISTA there. So they're talking about the software testing, but they didn't survey ISTA paper.
I'm not too familiar with the particular.
Yeah. So basically, I was asking with my knowledge. So of course, it looks into a lot of venue, and it is good. But if I'm the reviewer, I ask him, it is very weird that there's a conference called ISTA, which is top conference for software testing, but it is not listed there. And maybe the author may have a justification in the paper why the very traditional top tier software testing conference is not included. But anyway, let's keep going on.
So they also mentioned the types of the contributions, the main contribution to the paper as well. And they found that most of them were on new techniques and methodology. So this is not very surprising. Of course, most papers want to look at new fancy things rather than elaborating on existing techniques, for example. And most popular support effectiveness enhancements. So again, you have some new technique that improves an old technique, for example, the kind of thing. So these are not very surprising results, but still good to have them confirmed, I suppose.
Sorry, so can you be more specific on the type of contribution? So how do they support the category, the assessment, imperial studies, and how to distinguish the imperial studies and the case study? And is that possible that it only, or maybe it is, so they're looking to the papers in past 20 years, right?
Yeah.
Okay, so yeah, it's better to see, because for now, if we just conduct a case study, it is very hard for to write a paper or publish such paper just with a simple case study. So maybe 20 years ago, the researchers can do this.
The authors didn't really specify the exact difference in definition between empirical study and case study to answer your question about earlier, because they just mentioned as a note, as a passing note about the distribution of the contribution. They didn't mention the exact definition.
And then also my follow-up question is that sometimes a paper can fall into multiple categories.
Then which one do you put it in?
Yeah, so do they think these categories are exclusive or inclusive?
I think what they do is indicate they just choose the main contribution rather than if we have multiple contributions, choose the one that has the most part in the paper, I suppose.
Okay, so from these slides, we can see that I still have some doubt about the taxonomy, but overall, it gives us a big picture. And another indicator is that if we want to go to a survey paper, we probably need to multiple people. And also, there's a lot of dirty work to go.
Yeah, so quite a lot of number crunching in this paper overall.
Yeah, we look into all the literatures. Maybe I just feel that follow a certain template, survey paper can partially automate it. I just have such a sense. So we collect all the paper which has been published in 20 or 30 years and organize them based on keywords, and we generate graphs. Somehow we can write a script to do this. So it means that if we have such a scripts, maybe we can generate a survey paper partially through some scripts, which can largely improve the efficiency of the paper writing. That is just my gut feeling. Okay.
Yeah, so now we move on to the classification of the ART techniques. So this is a overall classification of the techniques used across the papers and what kind of techniques they are, what differences are, and how they are broadly used. So there are two basic rationales for techniques overall for achieving even spread of test cases. So the first is that new test cases should be far away from previously executed non-failure causing test cases. So this is what we talked about earlier, a reasonable assumption given that if we assume that failures are clustered, in the sense failure cases in the input domain are clustered into contiguous regions, then obviously we find a non-failure causing test case, you want to move as far away from it as possible to find a new failure causing test case. This is what this rationale is supposed to be for. The next rationale is that new test cases should contribute to a good distribution of all test cases over the entire input domain. So this is again going back to the even spread of test cases, that when you have a new test case, it shouldn't skew the distribution of the test cases across the input domain. These two are quite reasonable rationales for achieving an even spread of test cases.
I think they're basically the two different angles for diversity, right?
Yeah.
They want to generate the test case as diverse as possible.
Yeah.
And how to achieve such a high diversity. So they define the distance, right? They define the distance between test cases. The farther, the better. And also they define a distribution, and it's a more equal, the better, right?
Yeah, essentially.
Okay, well, let's keep going on.
Yeah. So before we go into the classification, talk about a little bit about metric they use to classify how well distributed the sample inputs are. This is called discrepancy. And the lower the discrepancy, the better for a test set. So how this works is that you have a measure of discrepancy by taking this value. So this maximum here is taken over all possible partitions of the input domain into randomly defined subdomains. And so basically the idea is that you have a domain, you split into subdomains, and their corresponding test cases, they are partitioned into different subdomains. And you want to make sure that the larger subdomains have more test cases and smaller subdomains will have fewer test cases. And the more your test set corresponds to this ideal, the lower your discrepancy will be and the better the test set will be. So this is a way of measuring the distribution of sample inputs. I actually wanted to give a concrete example, but the problem with this is that it's taken over all possible partitionings of the input domains. So it's not really feasible to give a concrete example in this case.
Yeah, this is quite abstract. Let's keep going.
Yeah, it's quite an abstract idea.
Oh, by the way, is there any questions here? Okay, so Darren, let me know when your question is coming. Yeah, let's keep going on.
Yeah, sure. So there are 7 different IIT techniques that are shown in these 140 papers. There are some acronyms used, but where possible, of course, I'll try to use the full name. So because I understand it's quite difficult to remember the acronym. So the first one is the canonical, so not really canonical, so-called most well-known ART technique, because this is the first one introduced in the original paper that introduced ART back in 2001. It's called a fixed size candidate set. So I say you have 2 sets. The candidate set C, which contains some K test cases. So the K here is a parameter that can be changed. It's just randomly generated from the input domain, and an executed set E, inputs executed without failure. So these are those non-failure causing test cases. So that is that first, in every iteration, you choose some element from the candidate set that's furthest away from all the tests in E. So this, of course, back to rationale 1, because the idea is that you want to choose the new test cases as far away from the non-failure causing test cases as possible. And the distance function is up to implementation. This is usually Euclidean distance in terms of some numerical vector. So you represent each test case as a numerical vector in some multidimensional space, and you use Euclidean distance for that. So this is an example here. This is audience question. So suppose we have 3 initial tests. So these 3 test cases that are executed without failure. And you have 2 candidate test cases, C1 and C2. So we pick for our distance measurement, we choose Euclidean distance, and we want to choose the test case that has the smallest, that's the largest minimum distance from all the other successfully executed test cases. So we see, for example, this is the distance from C1 to every other executed test case. And we look at the minimum of the distances between each test case and executed test case here. So in this case, which test case would you choose as the one with the largest minimum distance from black points from the executed test cases?
Yeah, that is good. That is good questions. Maybe Darren, we can point out on point and volunteer to address this question. Yeah, so we want to find the largest minimum distance. So there's 2 candidates. Basically, it's a binary answer, right? C1 or C2.
Yeah. So
anyone would like to have a try?
If not, maybe you want to give it a try?
Not quite get it. Sorry.
So basically, there's 2 samples. So each sample corresponding to a test case. So I think you find your work is closer to this one. So maybe in the future, you're going to synthesize the test code or derive a comment from the test cases. So basically a test case, we will define a distance. Each test case can be a data point in a space, okay? So we want to find the largest minimum distance. So basically, maybe Darren can further explain, or if you cannot do this, Darren can pinpoint or point to another audience.
Yeah, sure. I'll just give a quick explanation. So the idea is that we just go over what the points mean first. So the black points are just tests in E. So these are previously non-failure causing test cases that have been executed. And the white points are C, so tests in C, so candidate points. So these are the points that you're choosing from to select your next test case that you want to choose. So how you're selecting them is that you want to choose the test case with the largest minimum distance And so, for example, we look at this example here, we see 3 dotted lines here between C1, the rest of the test cases, and they have been executed. And of these, this is the smallest. So this is the minimum distance. And you want to maximize this quantity. So here we see 2 dotted lines here. We've identified the minimum distance for each candidate test between them and their nearest neighbor. And you want to choose the test case with the largest such dotted line. So which one should we choose in this case?
Okay, Darien can point on the point. You may suggest another audience.
Okay, in that case, maybe Xianghui, you'd like to try?
Hi, Xianghui. Hello, Xianghui, are you still there? Okay, Xianghui, since Xianghui is not there, let's ask another one. Darien, we can keep going on.
Yeah, maybe Rohan, would you like to give it a try?
Hi.
So it's C2.
Yes, exactly. So C2 as the largest minimum distance. So we choose C2, correct?
Okay.
So this is the idea behind it. Of course, you look at the minimum distance and choose. Of course, there are other metrics as well. So this is just one such a way of choosing. So it's and there are also other ways to choose. I mean, more advanced ways to choose, which we'll see later on as well, in different ART approaches. So the next one is called the select test from candidate strategy. So this is essentially kind of like a refinement of the first one I mentioned. So you generate the test cases first, and from this you choose a candidate set. So you choose a set of candidates from the input domain, and then you have some selection criteria. So this is a more refined version of what we talked about earlier. So instead of just the minimum distance, we look at other factors as well. And so every approach will have this kind of algorithmic black box, white box here, where we indicate the steps, and we have some boxes here that indicate components that we can plug in and out. So these are implementation details. And then so basically for every approach, we will first talk about the overall idea, the algorithm here, and then finally we talk about each component inside the boxes. So these are the things you can change in the algorithm. Yeah. So the next one here will be the random candidate set construction component. So this is the way we construct an initial candidate set, and there are different ways to do it. So one way, for example, is by uniform distribution. You just choose them from the input domain using a uniform distribution. Non-uniform distribution, so this is quite general. This is not really any real way to classify. It's just different distributions that different authors use. Then the next way is by filtering by eligibility. So in this case, we choose only test cases from eligible regions of input domain. So for example, we consider input domains split into regions. For example, some regions may have test cases not selected before. So for example, some regions have 0 test cases selected before from that region. And in the interest of getting an even spread, you want to choose test cases only from regions with no previous selection. So this is an example of filter by eligibility. Next case is a construction using data pool. So this is by using a data pool first, using some special values and boundary values. In this case, for integers, maybe we might have -1, 0, 1 for the special values, and boundary values being the 2 to the power 31 minus 1, for example, the min max for integers. And then we either choose our candidates from the data pool with some probability P that's a parameter, or from the entire input domain with the corresponding probability 1 minus P. And then we remove the candidates from the data pool until the pool is empty, and we refill the pool again and repeat the process until we have a sizable candidate set of required size. So this is a parameter, how big you want the candidate set to be. Finally, the last one is that we can achieve a specific degree of coverage. So this is that you just generate candidates repeatedly until you have some coverage criteria met. Next component will be the test case selection component. So generally there are 2 implementations. The first is that you grade all the candidates. So in this case, you have some fitness function. You just you grade all the candidates and see which one's the best one. You pick that one out. Either that, or you just check the candidates one by one until you find one that meets your needs. You just pick that one. So it's kind of like a lazier approach. So there are many different types of fitness functions. Just cover some of them that the authors covered in the paper. So these are the 7 different kinds. So these 6 here all repeat implementation 1. So we grade every single test case, and then we choose the best graded one. The last one here is the lazy evaluation. So we just evaluate the test cases one by one and pick the first one that matches our needs.
By the way, for now, we're just looking to the whole space of the black box, right?
Yeah.
So we giving the input space of the programs, we just keep sampling, right? We just keep sampling, define the distance and keep sampling. So this is basically all mathematical problems. But in terms of software testing, so there's more programming or more programming or software engineering problem. Maybe you can keep going on. Let's go through its methodologies, and I will give my comments later.
Yeah, sure. So of the first three, of course, it's quite it's quite intuitive. So we just choose the minimum distance. So E here is just the set of executed test cases as mentioned before. C is the candidate set. So we just choose the one with the minimum distance. Then we choose one with the largest such minimum distance. So this is of course very intuitive. It's been mentioned before. Same approach as the one from the first approach. Average distance is just the same idea, but instead of taking the minimum, we look at the average of the distances. So this takes into account, for example, one we have you're very close to one, but you have one very large, very far away from the other sets. You want to consider that as well. Then maximum distance is just in the other version, the inverse version of the first one. Centroid distance. So this is the idea that you have for E, you have this point which is essentially the center of all the points in E. And you want to measure the distance from the center instead of measure distance from the rest of the points in E. So it's just a different way of getting the distance, a gauge of how far you are from the set of evaluated test cases. And discrepancy here. So again, we talked about the discrepancy metric before, which is a way to measure the distance, the equidistribution of the sample points. So in this case, you want to choose the one that best maintains this equidistribution. This is just one way of doing it.
Sorry, can you be more specific on how they define the discrepancy?
Yeah, so this is quite far back actually. I'm not quite sure. I won't really go back to the slide because it's quite far back.
Yeah. So no need to go back. So discrepancy, where this inconsistency derive. So usually we need several test cases, right? So how to define the consistency? So how do we say one test case is consistent with another and when they're not?
Okay. So this is a bit of a misunderstanding, I'm afraid. This discrepancy does not refer to any kind of difference or variation in test cases. It's essentially a metric. The discrepancy here is specific to this context. It's a metric for measuring the equidistribution of the test cases.
Sorry, the equidistribution over
how well distributed the test cases are over the input domain.
Okay, so it's more like the uniform. Whether it's how uniform or how diverse of those test cases, right?
Yeah. So this fitness function is a way of maintaining the diversity of test cases.
Okay, so can you go back to the centroid one or average one?
Yeah.
So for average one, so I assume the C is actually a given test case, right?
Yes.
So given test case is want to see whether we. So the problem here is that whether we want to select C as a candidate.
Yes.
Right. So in this case, you need to measure the average distance of every test cases, which has already sampled. Right.
Yes, exactly that.
And in that case, so I'm not sure whether maybe I somehow get it. So basically, the larger the distance, the better. Right.
Yes. Yes.
And then basically all the measurement telling for the diversity. So they're using different kind of measurement for the diversity, but empirically speaking, they basically are all the same.
The same goal overall. Yes. To just improve
and I think
different ways of doing it.
I think there are no much difference from the final empirical results.
Yeah.
But they just taken different approach there. Okay, let's keep going on.
So this one's a bit more complicated. It's kind of fuzzy logic. So you have these two ideas. It's basically you score test cases higher if they maintain a certain minimum distance between test cases, and they maintain an absolute minimum distance as well. And with these two criteria in mind, you choose the one that best fits these two criteria. Yeah.
DMSD and AMSD, two criteria.
Yeah. It's a bit abstract, so I'll probably just not really go into detail on this one because there's quite a lot to cover as well, I realize. Yeah.
Okay.
The last one is just restriction.
Okay, please go on.
This one is just this one refers to the lazy evaluation mentioned before. So we just evaluate our candidate test cases one by one until we find one that suits our needs, one that meets the fitness function requirements, and we just pick it out and we stop evaluating. So this is why it's written.
And how do we define the restriction?
So this is again quite general. It really depends on the test cases. There's no set way because it's just across 140 papers. All the people using this approach do it differently.
So do they raise an example for the?
Fortunately, I don't think they raise an example for this one.
Okay, so let's keep going on.
Next will be the partitioning based strategy. So this one is a slightly different approach. So rather than generating a test case as a candidate set and then evaluating candidate set, this one instead we split the subdomain, the domain into subdomains first. So each input domain is now split into different domains. Then we pick out a subdomain to choose test cases from. So it's kind of like a reverse instead. And again, we have this is the algorithm again. We have two components. One is how to partition the input domain into different subdomains. And given this partitioning, how do we choose our subdomain that we want to pick our test cases from? So these are two components that we're looking at. So first is how to partition them. So there are two types of partitioning in general: static partitioning and dynamic partitioning. So static partitioning is that you partition once at the start of the entire procedure and you don't change partitions ever again. Whereas dynamics, you change partitions every iteration of the procedure. And for dynamic partitioning, there's three different types of dynamic partitioning: random partitioning, bisection partitioning, and iterative partitioning. And so the random partition is that you just use the test case as a breakpoint to split the domain. And you keep doing it repeatedly until you have enough domains. For bisection is that you bisect the partition along a dimension. So in this case, you assume you have some kind of multi-dimensional input domain. You split the input domain along a dimension until you hit certain threshold. So maybe you have 2 to the power I, where I is some integer number of partitions. Then you choose a different dimension and start again repeatedly. And finally, you have iterative partitioning.
So sorry for interrupting. So for this, I think this really makes sense for the partitioning. So in my mind, one of the very, very strong example is that we partition the test cases according to their the covered branch, right? So this basically fall into the category of static partition. That means the test case covering the same program branch will be partitioned altogether. So that is what we learned from the software engineering or software testing courses. It is usually undergraduate courses. And as for the dynamic partitions, I was still trying hard to find an example. So you say the random partitioning. So it is a default solution, but I would be more specific on when we need to partition the test case based on the runtime information. Is there any examples for that?
Unfortunately, no, there isn't. They don't give concrete examples for this one.
Yeah, otherwise I just feel that I understand. So we look into these concepts, but especially for the students with little software testing background, I feel that this kind of maybe it is not your problem. This is a survey paper in software testing. So, but anyway, since this is a discussion, this is a group discussion, I hope everyone can take the best of these talk and tutorials. So I will try to keep interrupting and complement some concepts. But here I feel a bit, I have some difficult time to think about examples and why we need to do the dynamic partitioning and what the benefits allow us to make such a partitioning.
Yeah, I understand. I completely understand your concerns about this. It's also quite abstract for me as well. So I'm having some difficulty when I wrote the slides as well. Unfortunately, they only give examples of papers where they do things, but they don't go into in depth about what the paper exactly did. So it's a bit difficult for me to follow as well.
Okay, let's keep going on. If you do not have the answer, let's keep going on.
Yeah. So next is the subdomain selection component. So given a certain partitioning, according to either static or dynamic partition mentioned before, how do we choose the subdomain that we want to generate our test cases from? So there are some criteria you can use to pick the subdomain. Split. You can see the colors here indicate whether or not you require the subdomains to have the equal size or not equal size. So this is just a requirement on the choice of strategy that you pick, essentially. So you can choose the maximum size. So this again, you may pick the subdomain at the largest size. So this is obviously not a static partitioning, not for static partitioning, because then you just always pick one subdomain. So this is probably for dynamic partitioning. So you want to pick the one that's the largest size, and you want to pick test case from there to ensure a more even spread. So other possible strategies involve picking the one the previously generated test cases, which we talked about earlier.
Yeah. So here maybe we can skip this one. So this is about how do we choosing the subdomain, right? So, but the problem is that this is how I support it with the example. So I just feel this survey talking a very abstract way. I don't know how they squeeze these materials into it, but if I'm the reviewer, I will strongly require the authors to provide concrete examples and where this abstraction derive, and what if we want to crystallize these abstract concepts into the practical software testing guidance, and what can we do? So I would like to ask the authors to provide this information. Maybe we can skip this one. So we know that there's a way to select the partitioning, and the larger the subpartition, the more likely we can improve our test efficiency, right? Okay, let's keep going on.
So it's back to the algorithm mentioned here. Yeah. So next would be a test profile based strategy. So this is a completely different strategy. We generate test cases according to a test profile. So this is a predefined test profile that's already created for you before you use this process. And then you update the test profile after each test case selection. So of course, the biggest question is how we adjust the test profiles on each iteration of this process. And the idea is that you want to adjust the profiles to satisfy the following criterion: that the closer the test case is to a previously executed test case, so a successful test case, the lower the probability of selection. So again, this goes back to the same principle talked about in the rationale one.
I think that was what we discussed this before.
And then the further away it is from, this is just the complement of it, but the further away it is from your successful test cases, the higher the selection probability. And finally, you want to adjust the probability distribution to maintain these two features. Unfortunately, they don't give specifics of what kind of test profile adjustments you use or what kind of profiles you should use, but they just mention some that were used in other papers without going into specifics. So this is essentially it. Yeah,
personally, I don't. I understand there's a lot of criteria here, but I don't think I have, up until now, as a software testing researcher, I haven't gained enough. So basically, it's good to learn these criteria. It's good to see the practice and organize the papers. But in terms of information they extract from the papers, I just feel, I'm not sure how to describe it. But for now, I haven't got many takeaways from this paper for now. Let's keep going on.
The next one is unfortunately even worse. This is about quasi-random sequences. So this is again a lot of formalism without many examples. So I'm just going to go over this very quickly because the only thing we pretty much get from this is that this exists and people use it. Yeah. So the idea is that you have some quasi-random sequence. So is that you have some sequence with low discrepancy. So it's a good equally distributed points and low dispersion. So the points are not very far away from each other.
Okay, let's skip this one.
We'll just skip this compo. We'll skip this one.
Otherwise, the search base. Okay, we can keep going on this one.
So this one's more closer to home, so to speak. This one's a search-based strategy. Use some algorithms to achieve an even spread test case across the input domain. So I'm just going to skip the algorithm because I'm sure everyone in this point is quite familiar with search-based software testing. So for the evolution component, how you evolve the test cases population over time, they've identified 6 different approaches. So hill climbing is just essentially like a local search. You just use a single test set, you calculate the fitness and you shake it, you perturb it as long as the fitness value increases until you stop at some local maxima, and then you're done.
This is kind of similar to gradient descent algorithm.
Similar to annealing is that you have some initial test case, again a single initial test set. You construct a new test set by modifying some of the input variables, and then you check the two, compare the two. If the new one is better than the old one, you obviously pick the new one. Otherwise, you decide which one to use using some control probability function. So they don't mention what kind of function to use. It's just
I suggest so maybe we do not need to go through one search algorithms by another. So overall, my comments is here. So if anyone is not familiar, admittedly, I'm not familiar with the random board centroid Voronoi tessellations. I don't know about the last one, but I think for most of us, I think we at least need to know about hill climbing, and simulated annealing, and the generated algorithms. So especially the genetic algorithms. So this is very, very important on search algorithm for that. If some of you are not familiar with search algorithms, I suggest you learn this and equip it yourself with this kind of knowledge.
So for genetic algorithm,
so we skip those.
So I think the last 3 are the more unfamiliar ones. So simulated propulsion is essentially just using some kind of electrostatic mechanics to simulate the test case evolution. Local spreading is essentially you have an initial test set. You slowly move every test case repeatedly until they're all maximally apart from each other, and then that's your final test case. So that's an example of achieving the even spread again. Finally, the last one is the oddest one, I suppose. So here the idea of the concept of a Voronoi tessellation is that you have certain target points first. So maybe a drawing would be better here. So suppose you have some input domains. Here we use a 2-dimensional domain, and then we pick some input points. So here maybe we have 3 target points. And the idea of a Voronoi tessellation is a way to partition this space into cells where you choose the points that are closest to you. So in case, idea is that, for example, let's say we have some point here, maybe this point, and we compare this from this point to the 3 target points. We find that this point is of course closest to this blue point, right? So in this case, we say that it's in a cell corresponding to this one. And in this way, you group every point until you arrive at something maybe like in this case be like this maybe. So this would be, or maybe closer here, but in this case, this is a Voronoi tessellation. So it's a way of splitting the input domain into sets there, where each point is closest to this point compared to the other points. And that's a Voronoi tessellation.
So the point is that we want to find, this is an optimal, right? So when we talk about the search space, there's the optimal. We want to search through all the solutions in the space. So how do they choose the best? So this basically a search algorithm. And how do they choose the optimal? And how do they replace or find the best solution? So when I understand there's a partition about the space, right?
Yeah.
So assuming that we have a partition of a space and how this partition can facilitate the search.
Yeah, sure. That's of course a very reasonable question to have. Let me just get a pen. Sorry, the answer is okay. Great. Yeah. So again, we have this. So this concept with the Voronoi tessellation, a way of partitioning our input domain. So we start first with a. Why is it so small? My apologies. We start first with a number of test cases in our initial test set. So it's of size n. So we have maybe, let's say n is 4, maybe 4 test points. From this test set of test points, we construct our Voronoi tessellation. So in this case, maybe something like I don't know, something like this maybe. See, this is our tessellation. From each tessellation, we choose the centroid, so the center of each. So remember, if we look, maybe this is the center of it, of this cell, center of this cell, center of this cell, and these 4 centers constitute our new test set. So this is their way of constructing a new test set. Yeah, so this is just the way they do it.
Okay.
Yeah.
Okay, so basically there's a different way of exploring the space.
Yeah.
Yeah. So I think we can just go past these slides.
Yeah.
So but anyway, I encourage every student, if you're not familiar with hill climbing, genetic algorithms and simulated annealings, you need to go through Wikipedia and to understand. And there are more formal and a more popular way to derive to exploit the search space.
So finally, we arrive at a hybrid strategy. So this is a way of combining multiple approaches to improve either the testing effectiveness, so in case whether it can detect faults, or the efficiency, the test case generation cost, the time it takes to generate the first failure, for example.
Okay, so we can pass this one.
Yeah. So this one is a combination. So it's just different ways of improving in certain points. So in case when you generate the M test case, you divide the input domain. So it's just an improvement on the way to generate the test cases. So nothing very interesting here essentially. Then here you choose in the test case selection step for this part, the select test candidate strategy, you just evolve the test case until stopping condition and choose the highest minimum value test case. So in this case, when in a candidate set, rather than just picking the candidates directly from the set, you evolve the set repeatedly until a stopping condition. Then you pick the test.
I will give my comments, so maybe we can skip these because I think people can very hard to extract the takeaway to generalize the idea. So maybe we'll look into this. The ART is more effective than RT. Okay, so this is a comments for the beneficial of the adaptive one, right? Adaptive random.
So this is also not just the author's comments, but also some summaries from previous survey papers as well. So it said in general, previous studies have shown that ART is more effective than RT, and these are the strengths. So it's obviously got a more even spread because that's its purpose. It's the advantage over the RT. It's better detecting faults. Better code coverage, it's better reliability estimation, it's better at cost effective the time taken to find the first failure. So we'll look at this very specifically in that it's cost effective in this specific manner that it's faster in finding the first failure. But we will also see later on that there's some disadvantages, that it's actually slower in generating test cases overall. So in this case, you have to look at what criteria you want for your test case generation. So my authors mentioned that ART is overall generally better than RT, but it's not always the case that we should always choose ART over RT when we are looking at test generation. So certain weaknesses, one of them is the boundary effect, is that it turns out that test cases can be generated at the boundary of the input domain rather than the center. This weakens the effectiveness of ART. And the authors say that they're not sure why, and studies don't really give a reason why as well. And they also mentioned that there's a higher overhead for generating test cases. So this again, as mentioned before, is a consideration you should take into account when you're looking at whether or not you choose ART versus RT.
Yeah, let's keep going on. I just feel that this one time for I'm not sure how much we can go for the survey. I can almost make my final judgment of the paper. So yeah, so I'm the reviewer that probably ask all the author to go through the other major revision instead of accept this one. Yeah, so I will give my comments later. You can keep going on.
Yeah, so thankfully we are already out of the largely out of the conceptual stuff. This is more empirical numerical stuff now. So which domains of ART been used? So here we see that largely used to analyze numerical programs, which is makes sense because most of the approaches we saw earlier all look at the input domain largely as a multi-dimensional space Rn maybe. So this is a good way to use on numerical programs. But it also means that ART does not function as well on non-numerical domains, where it's not as easy to convert into a Cartesian space and apply all those nice algorithms we have. So here we see also that it's used a lot less in other types of systems as well. It's also used in other testing domains because you can use it as they use it as an improvement for these types of testing. So the idea here is that in these papers they say, oh, we want to use ART as an approach to improve our regression testing, our combinatorial testing, and so on. So these are the types of testing that we use as well.
Okay, let's keep going.
So finally, effectiveness of application ART. There's some very large table in the paper. I have not put it in because it's simply too large.
Yeah, let's keep going. Skip this one. I think the summary. I will give my summary soon. Okay.
Okay. So finally, we talk about the analysis of the empirical.
Okay, so this also run a lot of the ART themselves, right?
Yeah. So this the idea behind it is that
they run the tools themselves, or they just take the result of the other paper.
They took the result of other papers. So this is all from other papers.
Okay, let's keep going on.
Yeah, so most of them used either simulations or real programs, and very few of them only use both. So we found that simulations are actually quite limited because the simulations simulate only numerical input domains. So we saw before, numerical input domains take up 47% of all the programs it's used on, but not the majority. It's not over 50%. So this is a big limitation. They also assume some failure patterns that may not be realistic. So in this case, you have to make some assumptions when you create the simulation about the types of failures you'll get and the patterns of the failures. And this may not always be realistic. So finally, we also have the simulations that account for test execution time. In case the simulation typically just has a static execution time for the test case. It means that it's not.
Yeah, let's skip this one. Yeah, I understand there's a lot of limitation. There's okay.
So we look at three parameters for simulator design. So the number of dimensions, the failure rate, the failure pattern. And so these are the values taken from the study. So this is a review of all the 73 primary studies, what kinds of parameters they use for the simulations.
Okay, let's keep going on. Yeah, we skip this discussion. And
finally, the authors mentioned that only one paper looked at 5 types of failure patterns in the simulation. So the rest only focused on a few failure patterns. And it means that the authors conclude that many studies have not designed the simulations comprehensively enough to accurately evaluate ART. So this is one of the findings about papers in the field. Next, we look at the programming language distribution of real programs. So this is again just some data, not very important.
Okay, skip this one. Yeah, so let's skip all of these numeric issues. So when we're looking to the survey papers, what we want to take is that the overall ideas of software testing and how generalized this survey can give us. I just feel that
this is all largely numerical.
I just feel, frankly speaking, so I feel a little bit disappointed about this paper. And basically, I believe that these authors haven't touched the insight of the software testing, and what is they have little idea of what the real challenge of software testing. They just look into the numeric problems. So maybe let's go to the author's point of what they want to do, and what they want to do about, and what does author believe it is a research direction, future research direction.
Yeah. So this is the last part essentially. So it's like open research challenges for ART. So they mentioned guidelines for simulator design. So in this case, they mentioned reliable guidelines on how to design the simulation. This is an open problem. The fact that there's a few investigations on the favorable and unfavorable conditions for each ART approach, and empirical studies on this are also lacking as well. There's also little research of ART applications to other input domains, so non-numerical domains mentioned before. Finally, they also mentioned that the ART approaches are largely theoretical in nature. They don't really focus on how effective, how efficient it is. Well, and finally, the lack of framework. So this again is a lot of things.
So what kind of tool they're learning to? So I think they have a good title of the paper. But anyway, so here the field tool. They think there's a field tool support ART.
Yeah. So they are actually
how can they get this paper accepted? I don't know. Let's keep going on. Yeah.
Yeah. So this is the end of it.
Okay. So anyway, so I just express my comments here. I just feel that despite this survey paper for software testing, but I highly doubt the authors have to conduct any software testing research, because they're talking about ART, they all talk about it in a very high level way, and they consider software testing as a pure numeric problems, and it just basically consider the software testing as a sampling problem, but actually it is not. I think the main difficulty is that how to numeric each software testing, each test cases into a numeric vector. So you can think about it when we write some Java or Python code, right? The input of the test is not numeric. It is usually a Java or Python object, or usually maybe we write a method. The input could be a session. If we run TensorFlow, it can be a session. If we use Java, it could be a hash map or array list. So it is no easy job to convert this object input into a numeric, into a number or into a data point in the high dimensional space. It is hard and almost impossible. And also we can input a graph, right? So if we input a graph and the structure is very dynamic, the graph can be very, very large, and the graph can be also very small. And its dimension, the number of dimension is not just fixed, it is extendable. It is also very flexible. So the problem is not that how to have a better, invent a better ART problem. I think the fundamental challenge is that how to turn these programming informations into a numerical problems to facilitate the optimization technique. So I think this is an ultimate problem. I don't think, I highly doubt the authors have conducted any software testing research. So they look upon the papers and do the summarizations, but they do not run the testing tool by themselves. So I just have this gut feeling. And also another challenge is that even if we can compare the distance of two test cases, and sometimes the test case distance of two test cases is very hard to measure. So assuming that the test case cover one path, one program path, and another test case cover the others. And how do we measure the distance, right? Suppose the branch is actually a is evaluating constraints for a non constraints. That means some variable should not be non. And how do we define the distance on such kind of branch? So that is also very, very hard to define it. So the problem, I don't think it is the problem mentioned this, but I don't know why TSE can get this. I don't know. So if I'm the reviewer, so these papers still need to go through some fundamental research or revisions instead of being in good shape to be published. But I really appreciate the author's effort to include so many papers. And I guess that as long as they get a major revision, as long as they also get a major revisions and they grasp every questions they address every question proposed by the reviewers and keep revising it and finally get accepted. I'm not sure how long it takes for the authors to do this, but anyway, they did a they did a good job to publish it. Yeah. Okay, let's keep going on. Yeah. Okay. So I have finished my
So
comments.
this is the end of the,
yeah. Is there any comments or suggestions or questions for this paper? Okay. If there are no questions, let's turn to let's thank Darien and let's turn to Alvin to provide a tutorial of ANTLR. I think this tutorial is supposed to be a more interesting one. But anyway, Darien did a very good job for presenting it. Yeah, we really appreciate it. But I think the paper itself may be a little bit problematic. Yeah. Hi, Alvin. Alvin, can you unmute yourself?
Hi, Prof. Okay, yeah. So I will start. Hi, everyone. Today I will go through a tutorial of designing your own language using ANTLR. I've taken the materials from the book, defining the definitive ANTLR for reference, and also a website that actually show you how to build an interpreter without using any kind of framework.
Okay, so before that, I will raise a simple question. What's the difference between compiler and interpreter?
Okay, interpreter is it translate a language without actually going to machine language. While a compiler will translate a language into a machine language. That's why I understand the difference between an interpreter and a compiler for execution.
Okay, so anyone have the other idea? Yufan, hi Yufan, you still there?
Yes, could
Yeah,
you?
yeah. The question is, do you know the difference between compiler or an interpreter?
In compiler and the interpreter.
Yeah.
Yeah, actually, I don't quite understand it. Could you explain to us?
Okay, so basically it is about the runtime. I think Alvin touched the point. So if I'm the one who give an answer, it is more about the runtime. So basically both tool is going to translate from a high level language into a low level language, and then it will be feeding to the machine to really execute it with the instruction, right? And the compiler basically is going to translate the programs translate the whole programs all at once, and then the machine is going to execute the translated execution. In contrast, the interpreter has ability to translate the high-level languages while executing it. So am I make myself understood? So interpreter, for example, Python or some version of Java. So when we executed the source code, right? We should, especially when we debugging the programs, we debug the program line by line. In this case, sometimes the internal strategy is that it will interpret the code each time we run it. So the source code which has been run will not be translated. Only the code, only the running code will be translated into machine code to execute it. In contrast, the compilers have to compile all the source code into the binary code so that it can be executed.
Okay, thank you.
So usually the interpreter is used for script like Python's. So the Python script we run, we execute it step by step and instruction by instruction. And especially for C++ or C programs, we have to using some compiler like GCC to compile or translate all the code into a .o or .exe file so that it can be executed. But usually a lot of compiler have two modes, the compilation mode and the interpretation mode. So I think the modern compiler can do both usually. Okay, let's keep going on, Ivan.
Okay, so Prof. Ling already summarized what ANTLR is, but I will just go through. It's a parser generator to read, process, execute, or translate structured text or binary files. Or in other words, a parser is a compiler or interpreter that breaks data into smaller elements for easy translation to another language. But to actually maybe give a feel what it really is, this is a Python command line interpreter. If I were to do 7 plus 4 that we always do, it returns 11. But question is actually, what is happening? Why is it if I do 7 space all the way plus 4, it also returns 11? But if I were to add 7 into a string there and plus 4, it will return something like a type error. Must be string or not integer. However, if we go into maybe like a JavaScript interpreter, you can see that actually 5 plus a string 3, it gives you 5, 3. What happens is that it concatenate 5 and 5 that is an integer and a string that is 3 together. So basically, a parser actually, it will break down a string into its respective what you call tokens, build a parse tree, and after that, there are transformation rules that actually produce the output. Each of their JavaScript, Python will have all their own transformation rules. So ANTLR, it gives you the method to actually produce something similar to this kind of interpreter or compiler. So who should use ANTLR? And what do you need to know? Programmers who are interested to build data readers, language interpreters, and translators. Basically, like what Prof. Ling mentioned is that you have a set of languages or you have a lot of data strings that has semantic meaning. Semantic meaning, for example, if in equations there is multiply sign, divide sign, subtraction and minus, how does the interpreter know which to prioritize the arithmetic expressions first? All these have grammar patterns in them, semantic meanings. You have to understand them to build your own grammar. After you build your own grammar, you will implement specific language applications based on these grammars, while it's going through the tree being built to execute it. I will go through in greater detail so that you have a better idea. So for ANTLR framework, given a grammar file, ANTLR will take this grammar file to generate something called the intermediate code. It can be in Java, Python, or C++. The intermediate code basically comprised of lesser parser, tree parser, listener, visitor. For the last two components, tree parser and listener and visitor, some of them call them interpreter, but now I listen properly, maybe I'm not so sure whether is it fully accurate or not. But that's what I see in some cases how they label it. So the intermediate code will take something like input string like 3 plus 5. And it can, based on how the user configure the transformation rules inside the listener in the visitor, the output can be 8 or maybe 3, 5.
So maybe I have some comments here. So I'm not sure whether any of you learned the course of compiler principle. So I think a lot of us are doing software engineering research. So usually I will ask myself, what is the best software engineering tool ever invented? So usually compiler will always be the first one coming to my mind. So usually software engineering research are going to inventing tools and methodologies to relieve the burden of programmers. So in terms of the contribution of such an effort saving, in terms of saved effort, so compiler will always the one who allows more people to take a job of programmers. Otherwise, the people will have to look into the registers, memory address, etc., which lower the program efficiency quite a lot. So Evan, can you go back to the previous slide? Yeah, for these ones, in terms of compiler principles, so usually they will have two components. One is about the syntactic analysis. So it's going to analyzing on what is the correct format, whether the high-level language, the supported high-level languages. So anyway, the input of compiler is actually a high-level language. The output is actually a low-level language or executable low-level languages. So executable means that this language is too simple to be executed by the machine. Usually it means an assembly code or it means binary code. So basically they're quite the same. So for compilers, usually a compiler usually consists of the syntactic component and then the semantic component. And a syntactic component usually analyzing the support, whether given a source code file, whether the source code file actually conforms to the correct grammar. For example, when we write a Python, write a Java, or writing C++, whether the programmers follow the rules to write the source code. So that's about the syntactic analysis. And once the syntactic analysis is put to correct, then we're going to translate the source code into a binary code and to execute the program. So that is about the semantic part. And here, I think the tree parser was still a part of the semantic analysis. So basically, it's going to define, in terms of tree parser and the listener, it will define various of the rules of translation, right? So when we translate the programs and we will define rules how to perform the translation, and after translation and what is rule to execute it. So once I discussed with a professor in UCLA, so one of the undergraduate course, an undergraduate course project is going to translate to let the students to execute a modified Java version. So a lot of students will know how to write Java, right? So they provide another version of Java, and the grammar is a little bit different. They're going to analyzing the grammar of the Java prime, the source code, and compile it into a register-based binary code. Okay, maybe I go too far here. So overall, the idea is the lexicon parser basically the syntax analysis and tree parser, listener visitors, maybe the ZS component for semantic analysis. Okay, let's keep going on.
Okay, so what happens that inside ANTLR, first that from the string, the character will be streamed towards a lesser analysis. Actually, like what Professor say, do the syntactic analysis to check that the characters inside the string all can belong to a token. After the string are converted into tokens, next parser analysis is a semantic analysis part. We'll try to determine the position of the tokens to be placed while building the tree. Finally, tree traversal will occur once the tree is being built, because there are transformation rules inside the listener or visitor in the ANTLR framework to actually convert all these values inside the nodes in the tree to output. Eventually, at the root node, you will produce a test output that is relevant to how the user set the transformation rules. So now I go through in detail what each of these parts mean. For example, the grammar specifies the syntax of the language, consists of a sequence of rules, mainly the parser and lesser rules. Basically, it tells you what can be considered as part of the language that your ANTLR framework will accept. This is an example of a grammar rule. When you look at a grammar rule, first thing you have to ask yourself is, what do you want your grammar rule to do? For example, this grammar rule is supposed to perform multiplication or division using just 2 integers. From here, you can see that actually there are 2 parser rules, which is the expression and the factor, and one lesser rule, which is the integer, or rather also known as a token. Parser rules are usually in lowercase, lesser rules are in uppercase. Therefore, to design a grammar first, after you have a rough idea what you want to do for your grammar, you have to come up with a few samples. Like, for example, in this case, it is 1 times 2, or maybe 4 divided by 3. All kind of examples that come out with how many spaces in between the strings. It will help you to design your grammar faster. So right now what I'll do is that I'll just go through quickly a few examples of grammars so that you have a feel how to interpret this. Over here, this is the most basic one. Is a rule, parser rule called R, that is supposed to identify a string hello followed by a lesser rule string. So you can see that it's supposed to recognize phrases like hello part, hello world, but there must be a space between the string hello and the next word. And if you put another word after the hello world, it will return an error. Back to earlier what I mentioned, this is a part that the simple multiplication division between 2 integers. I show this again because I want to highlight the next part over here, which is the green color portion. You can see that there's open and close parentheses for the rule expression with an asterisk sign there. It simply means that you can perform 0 or more arithmetic operation using multiplication or division. So how do you interpret any rules that has open and close parentheses and a star? Basically, the rule expression can be interpreted as the rule factor optionally followed by asterisk or a divide character followed by a rule factor, and it can be followed again the whole process like recursive, so on and so forth. That is how you can interpret the rules. There's also the plus sign instead of the asterisk. It means instead of an asterisk here, there's also a plus sign. It means 1 or more. As mentioned earlier, there are semantic meanings. This is a bit more complicated. I will go through it right now. So how do you convert a grammar for ANTLR to generate intermediate code? On the left hand is the normal way that usually everyone will write their grammar. This is the grammar code itself. You can see that inside the parser rules over here, is almost copy and paste the rules into the parser rules for the grammar to be accepted by ANTLR, along with some lesser rules. int is the integer from 0 to 9. WS rule is actually to ensure that the program will skip any space, text, or new lines. Now I just go through a quick example of some useful commands to understand your grammar design. So there is the Python implementation. There is also the Java implementation. I will just share what's the disadvantage. For me, I prefer Python, but I show Java because there's an interesting feature to show in Java. I'll first show in Python. So this is the rule earlier that I mentioned. So first you create your grammar file. After you create your grammar file for inside ANTLR, in any new terminal, after you have, I left an installation guide how to install ANTLR for you to set up. After you have installed it once, all you have to do for any new terminal that you open is just copy these few lines into there for it to remember the path. So right now you can see that I still only have the grammar file inside. Now I'm going to generate the intermediate files using this command over
by the way,
here.
ANTLR is supported by Java, right?
Yes, it's original code by Java.
Okay.
So actually the features will be much more advanced in Java compared to Python, but they have at the end for the translation of the code, they are both the same. So this command right now I will generate the intermediate files. So maybe I just filter out the files so you can see what is the files of interest. So you can see that it generates a lessor file, a parser file, and a listener file by default. Now I'm going to just.
Yeah, so here I have a comment here is that for now, usually if we want to write a compiler, right? So we need to handle a lot of stuff, maybe the lexer analysis, the syntax analysis, and the semantic analysis for that. So there's a lot of work. For ANTLR, it's basically a framework for us to define our own languages and generate the code. So Alvin, can you open one of the code of Lexa? So grammar Lexa.py. Yeah, so you can open one of them. Yeah, I mean open. I mean, so this is Python file, right? So I mean that you open the code.
Yes. I open the code.
Yeah, you can see. So this is just a Python code, right? And this Python code is almost automatically, basically is automatically generated. And this code, this Python code is basically Alexa to parsing the the tokens or the grammars of the language you defined. Okay. Is there any question here? If there's no question, let's keep going on.
Okay. So what happens is that there are a few functions over here. One is called so first I'm going to show you how to actually check. You can use something called parameter tree and parameter tokens to check that your grammar is breaking up the string to the correct tokens and also building the right tree. So I will show the tokens first. One plus 4 times 2. So you can see that right now it generated out, it shows you that it has seen 1 as 5 over here. What is the 5 representing is that it is representing the factor. So 1, 4, 2 are all represented as the factor. So from this, if there's no error, you can see that you have already designed that your grammar is accepting the tokens properly. Now the question is.
Sorry, Alvin. So can we be more specific on the 5? What does 5 mean?
Okay. Let me open up. So the 5 over here, you can see tokens inside grammar 1, there's a token dot tokens file. And what happens is that it helps you to identify each of these inside your string, what it represents, the category like
I
5
got it. I
represents
got it.
INT.
5 is a type, right? 5 is actually a type of token, right? Okay.
Yes, it's a
So
type.
it's not a semantics. It does not mean that 1 plus 4 is 5. So okay.
Yes.
And what
So
about T0, T1, T2, and T3? And that
T0, T2, T3, T4, honestly, I didn't go that far to really explore it, but the weapon is that you can see white space and others, they have already identified. T1, T2, T3, I'm not really fully sure.
I think it's still kind of a type. I think it is defining the. So can you let me check about the your BNF or the grammar you define, right? So
This is a grammar there.
yeah, I
this
think there's some terminals. Let me think about it. The int ws factor. T supposed to be can you compare the grammar dot g4 and grammar dot tokens? Yeah, so you can see there's some I guess so. I just guess that the so let me check about it. I think it's supposed to be, I guess, so I can only have a guess. That is about the, maybe it is non-terminal. I just say maybe non-terminal, non-terminal, maybe expressions and a ton. That is non-terminal. That is just my guess. I cannot guarantee that. But obviously, so giving this grammar, there's plus, minus, multiplication, division, and they're corresponding to yeah, so wait, Alvin, so on these operators corresponding 1, 2, 3, 4, 5, 1, 2, 3, 4, right? And the T0 to T3 are all still 1, 2, 3, 4. So are they there? Is there an overlapping there? So
this
if
part I have to double check itself
because the number refers to the token type, right?
Yes.
Right. So the int basically it is a token type. Yeah. So let's keep those details. If we want to do this, I think there's more menus and tutorials and documentation for us to refer to.
Okay.
Okay.
Okay. So the next part after the tokens is the tree. So it's a bit hard to see, but you can see that it groups the 4 and the 2 together for the Python. But in Java, it actually helps to give a clear view about the semantic meaning. So I'll just right now quickly show in Java. So at this stage now, you can see that there's still only a grammar file inside the Java folder. If I were to press this command, although it produces a Java file, it's still not sufficient yet because there's still one more step that needs to be included.
Yeah, so compared to Python, Java is more like a compiler, right? JVM is more like a compiler, and Python is usually called interpreter. So if for the students who are familiar with both Java and Python, so you can see in IntelliJ, it will ask us to specify the path of Java compiler, but for PyCharm, it was saying that it specifies the path of Python interpreter, right? So this basically is showing the difference between the Python and Java. Python is more like an interpreter and Java is more towards compiler.
Okay, so I execute this statement.
Mm.
So you can see there's the class, everything appear, and now I can
Mm.
run the.
So you can see, so if we
command.
want to run Java, we still have to compile all the project into .class file so that we can run them, right?
Yes. So okay, now I run the GUI program. So if now I will do something 1 plus 4 times 2. So you can see that it will generate to me quite a pass tree itself for me to identify. So basically, if we were to read the tree, how to interpret it will be 4 plus 2, 4 times 2, 8, then 8 plus 1 become 9. So if I were to change the order, the tree will also the structure of the tree will also change. Basically, therefore, you can use the token and the tree and the GUI especially to check your semantic meaning for your grammar in order to avoid any mistakes or something along the way that later you cannot figure out what's the issue with it. So I will go back now to the slides. So what I've been talking about so far is first syntactic analysis and semantic analysis to build the tree. However, the last question is how do we get the value 9? Like just now I show you where you build the tree there, but the question is how do you include a portion to return 9? Which is where the transformation rules come into place that you can either do through the listener and visitor. Listener is the option that will be generated by default in Python there, and also Java. It will generate a method for each of the pass rule with an enter and exit method. I'll show the file later so that you have a clear idea. But the tree walker cannot be controlled and needs to visit all the child nodes. For visitor, it will have a visit method per one rule, and the tree walker can be controlled. It does not need to visit all child nodes. This right now may not be quite clear what it means, but I will show it in my example next. So the first one I will go through a simple example is that use grammar to use listener to transform a short array initializer into the following string over here. So what you see is that basically after the string has been converted into its respective tokens, it further process that it convert the open and curly braces into codes and the value into a slash hexadecimal format with 4 digits. So right now, what I will do is that I will generate it like before to generate only a listener inside. So you can see there's a listener file only without a visitor. Let's take a look what's inside the visitor file. What's inside the listener file. So you can see that it helps you to create all the methods that are necessary to go through the rules, the puzzle rules. You can see there's an enter initialization and exit initialization. There's also an enter value and an exit value. So basically what you will do is that you use these methods inside listener to include your transformation rules. I'll show you quickly now how to do it. So this is the file that we're going to use. You can see that we will call the grammar2 listener to include the enter initialization and exit initialization. Each part over here, we will include a double quote to actually, when you enter the initialization node and exit initialization node, you will put a double quote there. And each time it cross a value, an integer value over here, it will transform the value into a hexadecimal value. So you can see that it transform in array initializer into its respective string over here. So that's how a listener works. You can see that it does not have much control over the different nodes and the rules. It's just basically over here, each of the rules, it directly implement the enter exit, and you're supposed to convert the values on the spot. It's for semantic problems like arithmetic conversion, expression, calculation, it will not be very practical to use a listener. Although, interestingly, they resolve the problem at the end. I will show you how. So now we will talk about the grammar for visitor. However, there's one thing I'd like to bring to your attention is that earlier I showed this grammar and the parsing rules and the lesser rules. Interestingly is that you can see that the parser rules over here is written differently compared to the BNF format. However, even though it's written differently, it will still have the same output and the same method. There's something I'd like to bring to your attention over here is that you can see that these are being I bold them actually. These are actually called label rules. I will show you what happens when you label the rules inside your grammar syntax in ANTLR. So to generate a command for intermediate code that only have visitor without listener, this is the command that you will use.
May I ask what's the difference between visitor and listener?
Okay, what happens is that for visitor, you see, just not for listener, if I were to try to implement what you saw just now, listener, to actually do arithmetic expression, is a bit difficult because what happens is that it does not really visit the nodes in a order that is, you can actually add the values together. That's why I will show right now. Actually, it'll be much clearer after this. Yeah. So give me a bit of time.
So maybe you can ask a follow-up question. So the visitor, so basically on the previous one, the listener is attached with the visitor, right? Once we visit some node in the tree, it will trigger some listener, right?
Yes, yes.
And here, so maybe I can recap the problem. The problem is that sometimes the runtime semantics or the operational semantics cannot be stick to the order of traverse on the tree. Is that the problem? So that means that if we want to look into the real one, for example, we want to calculate the expression. If we want to calculate the expressions and the semantic rule of how to handle some complicated or hybrided the operations, it may not necessarily follow the rule of traversal. Especially, it becomes very, very complicated. So we somehow need a way to decompose the trees into simplified version and execute the simplified version or intermediate representations in our own way.
Yes, because
please.
Yeah, because what happens is that, like you mentioned, the tree traversal part. I'm still not very familiar to use the terminology. When you perform a tree traversal in listener, there's right now in the way the book showed the example for the listener, you cannot use it for arithmetic expression. That was why I choose to show a listener first that just convert strings that is very straightforward as compared to a tree transversal for arithmetic expression that there's some parts behind it that it will be clearer after I go through the visitor program.
Yeah, so when do I understand you have already done a very good job for the presentation, but if you can raise more examples through slides, it'll be even perfect.
Okay.
Yeah, even more perfect. Yeah.
Okay.
Please go on.
So for the grammar itself, you can see that earlier I mentioned about the program rule. You can see there's a visit program. However, for the visit expression rule, there's no visit expression here. Instead, it has visit multiply, divide, visit addition, subtraction, and visit integer. It's because that when you put a hash and a comment after that, a hash and a string, it turns that any rule it has into sub rules for the visitor to access each of them separately. That was the part that actually I mentioned earlier. Visitor, you can control the child nodes transversal as compared to listener itself.
Okay, so maybe I have a comments here. Any of you are familiar with design pattern, right? So this is basically a source code, which is the converted or translated source code is basically correspond to a very, very classical design pattern. So if you learn Java, Python, etc., or C++, so I think design pattern is actually a course, integrated course in computer science. So if we want to visit a tree data structure, usually we're using the visitor pattern to do the job. But I cannot expand because it's more about how to use or write languages, write a concise program based on the features of object-oriented programming language. I will not expand it too much here, but I just make a comment here. So this is a visitor pattern follow the style of the object-oriented program language. Okay, let's keep going on.
Okay. So with the just now what I show about the visitor file, you can actually write inside the transformation rules inside like visitor multiply divide. It will take the left right node of the during the transversal to actually perform the operation itself. That was why actually just now when you ask the difference between the listener and the visitor, initially when they developed the ANTLR program, that was the main distinct difference between both of them. One of them can be used to transverse for semantic meaning, but the other could not be used to transverse for semantic meaning that it has to be in a certain order in order to transform the values properly.
So here I understand. So giving the algorithmic expressions, I think it's quite feasible to traverse based on AST, right? As long as, so anyway, if we want to calculate it, so given AST, we first need to calculate the value from the subtree. Then we recursively calculate the ultimate value. So this is what the tree stands for. But in terms of programming languages, we may do the same, right? So if the program is due, does every programming language follow the same style? Maybe yes. So by the way, for your master, for our DBI query languages, we're still using the tree parser to define such operational semantics.
Yes.
Okay, I see. Okay, thanks. Sounds reasonable. By the way, so Alvin, so is that possible for ANTLR to generate the intermediate languages? Is that possible? So
when you say intermediate languages, because the time when I understand about intermediate code, I look through an example online for one of the papers that actually said that the intermediate language of code is this kind of sorry.
Yeah,
Is
yeah,
all
I
these-
got it, I got it. So if you want to do this, we still, apart from design our own BNF, we still need to design the operational semantics of the low-level presentation, right? How to execute the low-level presentation. So if the tree can do the
yeah.
job, we do not bother to define another set of language. Yeah, you're right.
Yes. Okay.
Okay, keep going on.
So I just demonstrated that the visitor and the visitor is able to perform the arithmetic expression accurately. Maybe just one more. So I just switched the order of the operators over here, and they both give the accurate results. So the last one I'd like to just bring your attention to is the, other than paying attention to the way you write your grammar syntax file for ANTLR, it's actually possible now to do a grammar for both listener and visitor. However, listener, there's a bit of there's a trick there to actually make it perform the tree traversal like how a visitor will perform it. I will just open the code first to actually talk about it. This is the visitor. This is the listener. So you can see that, wait, let me open the grammar also. So you can see that the grammar is actually is to just either perform multiplication or addition, and E can be an integer, so there's multiply, add an integer there, and it starts with S that ends with E. So you can see that among the listener and the visitor, both of them have the common rules, which is multiply, add, and integer. And they actually look the same itself. They both have left and right, and multiply, addition, and also the integer. So what is the difference between the listener and the visitor? The difference is that visitor is able to perform the tree traversal and the calculations without needing to specify an additional variable. However, for listener, it has to verify the stack. So what happens is that during the traversal, whenever it goes through the numbers, it will push the number into the stack. And when it reaches a multiply or addition, it will pop out the numbers to perform the multiplication. That is how the traversal occur, like what Prof. Lin just now mentioned, the part there. That's how they overcome it after they did labeling of the rules to break it down further. Before that, they did not was not able to do this and they had to use visitor. So to actually conclude what I want to share about designing your language first is that you have to actually look at the book to understand all the different kind of possibilities that for one BNF format, they can write it in 2 to 3 at least different ways with visitor or with listener to implement it. And the last part is why you should use ANTLR is because this is a file that I found online before I know about ANTLR to do parsing, and is to perform the arithmetic expression. You have to first develop your tokens and your lesser rule. Finally, your parser rule.
Yeah. So I want to. So when I was an undergrad student, so I write an all by myself. But now we have such a framework of the tool, so we can generate all this code using machine, and then we just need to define the rule there. So that is very convenient for us to design our own language.
Yes. So yeah, that's all for my demonstration and design.
Okay. So I think it is very great. It is very good tutorials, and I think Alvin did a very good job here. Yeah. So hopefully we can further the studies, and after you join us as a research assistant.
Okay.
Mm.
Okay.
Okay.
Yeah, that's all I have for now.
Okay, so any questions for Alvin's presentation? I think it's fairly clear and very helpful for us to understand the basics. Of course, if we want to do our own languages, there's a lot of the more formal analysis. For example, whether the design languages is can form some property, right? So why we want to design language in such a way. So there's another kind of methodologies. But for today's presentation, it is just basically a implementation, a tool, a facility for us to use if we want to design our own language. Okay, any questions for Alvin for his presentations or for Darren? Okay, if there's no questions, let's call it a day. Thanks everyone for attending. Bye.